The morning of November 4th, 1940, began like any other test flight day at Wright Field in Dayton, Ohio. Major Signa Gilkey climbed into the cockpit of P-38 Service Test Aircraft No. 5, checked his instruments, and prepared for a high-speed dive evaluation. The aircraft beneath him represented 2 years of intensive engineering by Lockheed's design team under Clarence Kelly Johnson. Twin Allison engines, counter-rotating propellers, a central nacelle for the pilot with twin booms extending back to the tail. Nothing like it had ever flown before. At 11,000 feet, Gilkey pushed the nose over and began his dive. The Lightning accelerated smoothly at first. Then, approaching 400 miles per hour, the aircraft began to shake. The tail assembly vibrated with increasing violence. Gilkey felt the control column grow sluggish in his hands. The nose wanted to tuck under further, steepening the dive beyond his control inputs. He pulled back on the yoke. Nothing. The controls had locked up completely. The aircraft was accelerating toward compressibility, racing toward a speed where the air itself would refuse to flow smoothly over the wings and tail. Gilkey stayed with the aircraft as it screamed downward through 7,000 feet, then 6, then 5. His training told him to bail out, but something made him wait. At lower altitude, where the air grew denser, the controls suddenly came alive again. He pulled out of the dive with less than 2,000 feet to spare. 48 hours earlier, test pilot Ralph Virden had not been so fortunate. His P-38 had entered the same kind of dive during high-speed testing. The tail structure simply fell apart. Virden died in the crash. The accident investigation was still ongoing when Gilkey climbed into his aircraft that morning. Now, landing back at Wright Field with his hands still trembling, Gilkey filed a report that would force Lockheed to confront an uncomfortable truth about their revolutionary fighter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was not subtle. Every pilot who pushed a P-38 past 350 miles per hour reported the same terrifying sequence. Vibration, loss of control, a dive that could kill you if you did not reach denser air in time. The Army Air Corps grounded the entire test fleet while Lockheed engineers tried to understand what was going wrong. Wind tunnel tests at the California Institute of Technology began immediately. Engineers mounted scale models of the Lightning in the tunnel and subjected them to airflows simulating high-speed flight. They tried different wing configurations. They tested various tail designs. They measured airflow patterns over every surface of the aircraft. What they discovered challenged everything they thought they knew about their design. The XP-38 prototype, which had crashed in February 1939 after its record-breaking transcontinental flight, had been configured with propellers rotating inward at the top of their arc. The blades turned toward the cockpit, toward each other. This seemed logical. Most multi-engine aircraft used this configuration. But the wind tunnel tests revealed something unexpected. When the propellers rotated inward, they created a spiral wash of air that flowed back over the wing and struck the tail assembly at high speed. At 400 miles per hour, this propeller wash was moving fast enough to create severe buffeting on the horizontal stabilizers. The vibration Gilkey and the other test pilots had experienced was not a structural failure. It was aerodynamic. The aircraft was shaking itself apart from the inside because of how air moved over it. To understand why this mattered so profoundly, one must understand what the P-38 Lightning represented in 1940. The United States Army Air Corps had issued its specification for a high-altitude interceptor in 1937, requesting performance that seemed impossible. The aircraft would need to reach 20,000 feet in 6 minutes. It would need to maintain 360 miles per hour at that altitude. it would need to carry heavy armament, including a cannon. No single-engine fighter design could meet these requirements with the engines available at that time. The power simply was not there. Lockheed's response was radical. If one engine could not provide sufficient power, use two. Mount them in nacelles on a twin-boom configuration, leaving the center nacelle free for the pilot and a concentrated battery of nose-mounted guns. Use turbo-superchargers to maintain power at altitude. Counter-rotate the propellers to eliminate torque effects that plagued single-engine fighters. The concept worked brilliantly on paper. Lockheed received the contract in June 1937 for $163,000 to build a prototype. Construction began in July 1938 at Lockheed's facility in Burbank, California. The XP-38 first flew on January 27, 1939, with Lockheed test pilot Ben Kelsey at the controls. The flight went smoothly. The aircraft handled well. 2 weeks later, on February 11th, Kelsey attempted a transcontinental speed record flight from California to New York. He made the crossing in 7 hours and 2 minutes, demonstrating performance that exceeded every specification the Army had requested. But carburetor icing on the approach to Mitchell Field in New York caused the engines to fail. Kelsey crash-landed short of the runway. The prototype was destroyed. That crash meant the Army had to base its production decision on a single test flight and one spectacular cross-country dash. They ordered 13 YP-38 service test aircraft in April 1939. These would be production representative machines, built to verify that Lockheed could manufacture the Lightning in quantity, and that the design was sound for military service. Lockheed engineers made numerous changes from the XP-38 to the YP-38 design. They lightened the structure where possible. They revised the engine installation. And they reversed the propeller rotation. Where the XP-38 had used inward rotating propellers, with the blades turning toward the cockpit at the top of their arc, the YP-38 would use outward rotating propellers with the blades turning away from the cockpit. This decision was not made casually. The Allison V-1710 engine was designed with a modular architecture that made changing the rotation direction relatively straightforward. The engine used a reduction gearbox between the crankshaft and the propeller shaft. By reversing the gearing, Lockheed could make left-hand and right-hand engines that were otherwise identical. The counter-rotation was essential to the Lightning's handling characteristics. In single-engine fighters, the massive torque from a high-horsepower engine created serious control issues. A pilot taking off in a P-47 Thunderbolt with its 2,000-horsepower Pratt & Whitney radial engine had to apply significant rudder input to keep the aircraft tracking straight down the runway. The propeller torque wanted to roll the aircraft. In air combat, this torque made the aircraft roll much faster in one direction than the other. The P-38, with counter-rotating propellers, eliminated this problem entirely. The torque from the left engine canceled the torque from the right engine. The aircraft tracked straight on takeoff with no rudder input required. In combat, it could roll equally well in either direction. The engineering team believed they had made the right choice with outward rotation. Kelly Johnson, the brilliant young engineer who had shaped the Lightning's design, had calculated that this configuration would provide better stability for the concentrated nose armament. A fighter aircraft is most valuable when it can put bullets on target. The Lightning mounted 4 50-caliber machine guns and one 20-millimeter cannon in the nose, all firing straight ahead with no convergence issues. Unlike wing-mounted guns, which had to be angled inward to create a cone of fire at a specific range, nose-mounted guns simply pointed where the aircraft pointed. But this advantage only mattered if the pilot could hold the aircraft steady while firing. Any tendency for the nose to pitch up or down during combat would throw off the aim. Johnson's calculations suggested that outward rotating propellers would reduce the power-on, power-off pitching moments. When a pilot advanced the throttles from cruise power to full power, or when he pulled them back suddenly during combat maneuvers, the aircraft should remain more stable in pitch attitude. This would make the Lightning a superior gun platform compared to aircraft where propeller effects caused significant nose movement with power changes. The wind tunnel tests supported this theory. Models equipped with outward rotating propellers showed reduced pitching moments compared to the inward rotating configuration. But those same tests revealed the buffeting problem. At high speeds, the airflow pattern created by outward rotating propellers was different from the inward rotating pattern. The spiral wash of air moved differently over the wing and tail surfaces. Engineers at Lockheed and at Wright Field analyzed the test data for weeks. They measured pressure distributions across the wing surface. They studied photographs of airflow visualization tests, where smoke streams revealed how air moved over the aircraft at different speeds. They calculated the forces acting on the tail assembly at various air speeds and power settings. The conclusion was unavoidable. The inward rotating propeller configuration would have been better for high-speed flight. The propeller wash would have flowed under the inboard portion of the wing, between the engine nacelle and the fuselage. This airflow would have provided additional lift and created less turbulence over the tail. The outward rotating configuration, while better for gunnery stability, was creating a 40% increase in airspeed at the wing-fuselage junction, where the thickness-to-chord ratio was highest. At 25,000 feet, when the Lightning approached 500 miles per hour, that junction airflow was reaching transonic speeds. Shock waves were forming. The tail was being battered by turbulent air that threatened to shake the aircraft apart. This presented Lockheed with an impossible choice. They could reverse the propeller rotation back to the inward turning configuration, which would solve the high-speed buffeting, but would compromise the aircraft's stability as a gun platform. Or they could keep the outward rotation and find another solution to the buffeting problem. The Army Air Corps needed the Lightning. War was spreading across Europe. Britain was fighting for survival against the German Luftwaffe. American military planners knew that involvement in the conflict was becoming increasingly likely. The nation needed a high-performance interceptor that could match or exceed anything the Germans or Japanese could field. The Lightning was the only aircraft in development that promised that capability. Grounding the program or delaying it for a major redesign was not acceptable, and so the engineers went back to their wind tunnels and their calculations. They tried leading-edge wing slots to control the airflow. They experimented with various combinations of filleting between the wing, cockpit, and engine nacelles. They conducted wind tunnel test after wind tunnel test, searching for a solution that would allow them to keep the outward rotating propellers while eliminating the deadly buffeting that had killed Ralph Virden and nearly killed Signa Gilkey. Wind tunnel test number 15 at the California Institute of Technology began on a cold morning in late 1940. Lockheed engineers had mounted a 1/16th scale model of the P-38 in the tunnel, carefully positioned to allow measurement of airflow patterns at speeds simulating 400 miles per hour at altitude. They had tried 14 different configurations already: leading-edge wing slots, various combinations of fairings and fillets, modified tail surfaces. Nothing had eliminated the buffeting that was killing test pilots and threatening to ground the entire program. The engineer supervising the test that morning was running out of ideas. His team had been working 18-hour days for weeks, trying to solve a problem that seemed to defy every conventional approach. The buffeting occurred at high speed, but it was not a simple matter of structural weakness. The tail assembly was strong enough. The problem was aerodynamic, and aerodynamic problems required aerodynamic solutions. He had studied every available reference on high-speed flight. He had consulted with engineers from other aircraft manufacturers. He had even contacted the National Advisory Committee for Aeronautics for guidance. The answer kept coming back to the same fundamental issue. Airflow disturbances ahead of the tail were causing the horizontal stabilizers to shake violently at specific speeds. For test number 15, the engineers tried a large fillet between the wing and the fuselage, blending the two surfaces together with a smooth curve rather than a sharp junction. The theory was that this would reduce the turbulence created where the wing root met the central nacelle. They activated the wind tunnel and brought the airspeed up gradually. At the simulated equivalent of 250 miles per hour, the model sat steady. 300 miles per hour, still stable. 350 miles per hour, no vibration. 400 miles per hour, the tail remained rock solid. The engineers stared at their instruments in disbelief. They ran the test again to verify the results. Then a third time. The buffeting had disappeared completely. The solution was elegant in its simplicity. The fillet changed the airflow pattern at the wing fuselage junction, where the thickness-to-chord ratio was highest. Without the fillet, air accelerating over the wing surface at that junction created a pressure wave that propagated back toward the tail. At high speeds approaching 500 miles per hour at 25,000 feet, that airspeed increase at the junction was 40% higher than the free stream velocity. The air was reaching transonic speeds, creating shock waves and turbulence. The fillet smoothed the airflow, preventing the formation of those shock waves and eliminating the turbulent wake that had been battering the tail assembly. Lockheed immediately incorporated the fillet into the production design. Every P-38E and subsequent model would have this feature built in from the factory. For aircraft already delivered to the Army Air Corps, Lockheed manufactured retrofit kits. These kits were shipped to every squadron flying Lightnings, with detailed installation instructions. The modification was mandatory. Without the fillet, the aircraft was not safe for high-speed flight. With it, pilots could push the Lightning to its performance limits without fear of losing control. But the wind tunnel testing had revealed something else, something that the engineers had not been looking for but could not ignore. The tests comparing inward rotating versus outward rotating propeller configurations showed a significant performance difference. The outward rotating configuration, which Lockheed had chosen for gun platform stability, was actually faster. Measurements indicated a speed increase of 20 to 30 knots compared to the inward rotating setup. This was not a trivial difference. At high altitude, where the Lightning would be intercepting enemy bombers, 20 to 30 knots could mean the difference between catching the target or watching it escape. The propeller rotation direction was creating a propulsive efficiency advantage that the engineers had not fully appreciated when they made the initial design decision. The mechanism behind this speed increase took weeks of additional testing to understand fully. Engineers at Wright Field and at Lockheed's facility in Burbank worked together to map the airflow patterns created by different propeller configurations. What they discovered challenged some fundamental assumptions about propeller design for multi-engine aircraft. The spiral wash created by a propeller does not simply push air backward. It creates a rotating column of air with complex three-dimensional flow patterns. When two propellers rotate in opposite directions on a twin-engine aircraft, their spiral washes interact with the aircraft structure in ways that can either help or hinder performance. With outward rotation, the upward-moving portion of each propeller's spiral wash passed under the inboard section of the wing, between the engine nacelle and the fuselage. This airflow provided additional lift on that portion of the wing and created a favorable pressure gradient that reduced drag. The air was being channeled in a way that helped push the aircraft forward rather than simply being thrown back as turbulent waste. With inward rotation, the spiral wash patterns interfered with each other more directly and created less favorable pressure distributions across the wing surfaces. The difference was measurable in the wind tunnel and would be measurable in flight testing once the buffeting problem was solved. Kelly Johnson reviewed the data with a mixture of satisfaction and frustration. Satisfaction because the team had apparently made the right choice, even if they had not fully understood all the reasons at the time. Frustration because the full performance potential of that choice had been masked by the buffeting problem. The Lightning could have been demonstrating its superior speed characteristics months earlier if they had identified the Philae solution sooner. But there was no point dwelling on what might have been. The important thing was that they now had a complete solution: outward rotating propellers for both gun platform stability and maximum speed, plus the wing fuselage fillet to eliminate high-speed buffeting. The first production P-38E aircraft with factory-installed fillets rolled off the assembly line in October 1941. Test pilot Milo Burcham took the aircraft up for its maiden flight and immediately noticed the difference. He pushed the Lightning through high-speed dives that would have been suicidal in the earlier aircraft. No buffeting, no loss of control. The aircraft responded crisply to control inputs at speeds approaching 450 miles per hour. When he landed and climbed out of the cockpit, Burcham reported that the Lightning was finally ready for combat. The aircraft was everything that Kelly Johnson's original design had promised, but which the buffeting problem had prevented them from demonstrating. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Army Air Corps pilots began receiving their P-38Es in late 1941 and early 1942. The aircraft's performance exceeded their expectations. The twin engines provided redundancy that single-engine fighters could not match. The turbo superchargers maintained power at altitudes where other fighters struggled. The concentrated nose armament made gunnery straightforward compared to wing-mounted guns that required convergence calculations, and the speed, the pure straight-line speed that the outward rotating propellers helped deliver, gave Lightning pilots the ability to engage or disengage from combat at will. German and Japanese pilots who encountered the P-38 in combat learned quickly that trying to run from a Lightning was futile. The twin-engine fighter could chase down anything in the sky. The engineers who had spent those long weeks in the wind tunnel, testing configuration after configuration until they found the solution, never received public recognition for their work. Their names did not appear in newspaper articles about the Lightning's combat victories, but they knew what they had accomplished. The true validation of the propeller configuration and the fillet modification came not in the controlled environment of a test facility, but in the chaos of aerial combat. In the Southwest Pacific, P-38 pilots of the 5th Air Force faced Japanese fighters that were lighter, more maneuverable, and flown by combat-experienced pilots. The Mitsubishi A6M0 could turn inside any American fighter. Its light weight and low wing loading gave it performance advantages in low-speed turning engagements that American pilots could not match through skill alone. But the Lightning pilots discovered they did not need to turn with the Zero. The tactics that emerged from combat experience exploited the Lightning's speed advantage. Pilots would patrol at high altitude, using the aircraft's excellent climb rate and high-altitude performance. When they spotted enemy formations below, they would dive, building speed to over 400 miles per hour. They would make a single high-speed pass through the enemy formation, firing their nose-mounted guns at targets of opportunity, then use their momentum to climb back to altitude before the Japanese fighters could react. The Zero pilots would give chase, but the Lightning was already gone, racing upward at speeds the Japanese aircraft could not match. This became known as boom and zoom tactics, and it required an aircraft that could sustain high speeds and climb rapidly. The P-38, with its outward rotating propellers providing maximum speed and the filleting allowing safe, high-speed flight, was ideal for this combat method. Major Thomas McGuire, who would become the second highest scoring American ace of World War II with 38 confirmed victories, flew P-38s exclusively in the Pacific Theater. He described the Lightning's speed advantage in his combat reports as the single most important factor in his survival and success. When enemy fighters tried to pursue him after an attack, he would simply push the throttles forward and pull away. The Japanese pilots, watching the Lightning accelerate out of range, must have felt the same helpless frustration that test pilots felt when they realized their aircraft simply could not keep up with a well-flown P-38. McGuire's tactical doctrine emphasized using the Lightning's strengths rather than trying to dogfight in situations where the aircraft would be at a disadvantage: speed, altitude, and firepower. Those were the three advantages the Lightning provided, and the outward rotating propellers contributed directly to the first of those advantages. In Europe, the story was similar, though the opposition was different. German Focke-Wulf FW 190 and Messerschmitt Bf 109 fighters were formidable opponents with good performance at all altitudes, but the Lightning could outrun them in level flight and could sustain high-speed dives that German fighters could not match safely. Luftwaffe pilots who engaged P-38s learned that pressing an attack against a Lightning fleeing at full speed was usually futile. The American aircraft would simply pull away, leaving the German pilot with the choice of breaking off the chase or running his engine at unsustainable power settings that would cause mechanical failure. The speed advantage that the outward rotating propellers helped provide was not huge, perhaps 20 to 30 miles per hour compared to what the aircraft would have achieved with inward rotation. But in combat, that margin could mean the difference between escaping to fight another day or being shot down. Technical Sergeant James Warren, a crew chief maintaining P-38s with the 8th Air Force in England, later recalled that pilots returning from missions would praise the Lightning's speed above all else. They trusted that if a mission went wrong, if they were outnumbered or outmaneuvered, they could simply point the nose down, advance the throttles, and accelerate away from trouble. That confidence, that psychological assurance that the aircraft could save them when things went bad, was worth more than any amount of maneuverability. The P-38 Lightning entered full-scale production, with the design choices vindicated by combat experience and engineering analysis. Lockheed's Burbank facility expanded to meet Army Air Force's demand, while subcontractors across the country produced components for the complex twin-engine fighter. By 1943, the production line was delivering over 200 Lightnings per month. Each aircraft left the factory with outward rotating propellers and the wing fuselage fillet that had solved the buffeting problem. These features were no longer experimental. They were standard, proven, essential elements of the design. But Lockheed's engineers were not finished refining the Lightning. In 1942 and 1943, they experimented with further improvements to propeller efficiency. The standard Curtiss electric propellers that had been in production since 1941 worked well, but engineers believed they could do better. Hamilton Standard, the company that had supplied propellers to Republic Aviation for the P-47 Thunderbolt, had developed a new paddle blade design with significantly increased blade area. These high-activity propellers could convert more engine power into thrust, particularly at high altitudes, where air density was low and conventional propellers struggled for grip on the thin air. Lockheed obtained a set of these Hamilton Standard paddle blade propellers and fitted them to a test aircraft, a battered P-38E that had been used for various experimental modifications. The aircraft was informally called the K-Mule. Test pilots flew it to 45,000 feet with ease, demonstrating climb performance that exceeded anything the standard Lightning could achieve. Encouraged by these results, Lockheed modified a P-38G airframe more extensively. They designated it P-38K-1LO and fitted it with the paddle blade propellers. New Allison V1710-7577 engines, producing 1,875 horsepower in war emergency power, and a modified gear reduction ratio of 2.36 to 1 instead of the standard 2 to 1. The combination of more powerful engines and more efficient propellers promised dramatic performance improvements. Flight testing of the P-38K began in February 1943 at Wright Field in Florida. The results exceeded even optimistic predictions. Maximum speed at 29,600 feet was 432 miles per hour using military power settings. Engineers calculated that with war emergency power, the aircraft would exceed 450 miles per hour. The initial rate of climb was 4,800 feet per minute. The service ceiling reached 46,000 feet. Most remarkably, the P-38K could climb from a standing start on the runway to 20,000 feet in exactly 5 minutes. No other American fighter could match that performance. When Lockheed test pilots flew the P-38K against the latest P-51B Mustang and P-4070 Thunderbolt, the Lightning proved superior in every category of measured performance. Army Air Force's evaluation teams watched in amazement as the modified Lightning demonstrated capabilities that made it arguably the best piston-engine fighter in the American arsenal. Lockheed prepared to put the P-38K into immediate production. The company had the manufacturing capacity. The supply chain was established. Transitioning from P-38J production to P-38K production would require only modest retooling. But then the War Production Board intervened. They calculated that the changeover would interrupt Lightning production for 2 to 3 weeks, while factories retooled for the new propellers, modified engine mounts, and redesigned cowlings. During those weeks, perhaps 150 to 200 aircraft would not be delivered to combat units. The board determined that maintaining production flow was more important than incorporating performance improvements. The P-38K was never manufactured beyond the single prototype. The Army Air Forces continued to receive standard P-38Js and the later P-38L variant, both of which used the conventional propellers rather than the superior paddle blade design. The decision to use outward rotating propellers on the P-38 Lightning, made in 1939 and validated through years of combat experience, represents a case study in engineering decisions made with incomplete information that nevertheless proved correct. Kelly Johnson and his team at Lockheed chose outward rotation primarily to improve gun platform stability, reducing power-on, power-off pitching moments that would interfere with accurate shooting. The speed advantage was a secondary benefit that emerged from wind tunnel testing and was confirmed in operational service. But that secondary benefit contributed materially to the Lightning's combat effectiveness and to the survival of pilots who flew it. 20 to 30 miles per hour may not seem significant in the context of aircraft that routinely flew at speeds exceeding 400 miles per hour, but combat is decided at the margins. A pilot fleeing from superior numbers at 420 miles per hour will escape from pursuers flying at 390 miles per hour. The distance between the aircraft grows steadily, inexorably. After 5 minutes, the Lightning will be 2.5 miles ahead. After 10 minutes, 5 miles. The pursuing fighters must eventually abandon the chase or
run out of fuel trying to close a gap that continues to widen. This speed margin saved lives. Pilots who might have been shot down in slower aircraft survived because the Lightning could simply outrun the opposition. The contrast with what might have been is instructive. If Lockheed had retained the inward rotating propeller configuration from the XP-38 prototype, the buffeting problem might have been less severe or might not have occurred at all. The filly modification might have been unnecessary. But the aircraft would have been measurably slower, and that speed deficit would have cost American pilots their tactical flexibility. They would have been forced to engage in turning dogfights with more maneuverable opponents,
fighting battles that played to the strengths of Japanese and German fighters rather than to Lightning's advantages. Combat loss rates would have been higher. Fewer enemy aircraft would have been destroyed. The psychological confidence that P-38 pilots felt, knowing they could disengage from unfavorable situations, would have been diminished or absent. The P-38K represented the ultimate expression of what the Lightning could have been if production priorities had allowed. Its paddle blade propellers extracted every possible advantage from the outward rotation configuration. The speed increase compared to standard P-38J aircraft was 40 miles per hour. The climb rate improvement was over 1,000 feet per minute. These were not marginal gains. They represented a generational leap in performance. But the War Production Board's decision to maintain production flow rather than interrupt it for retooling reflected a different calculation of what mattered most. Better to have 200 adequate fighters than 150 superior fighters, they reasoned. Quantity has a quality all its own, particularly when the adequate fighters were already proving effective in combat. This tension between optimal design and production reality characterized American aircraft development throughout World War II. Engineers could design magnificent machines that pushed the boundaries of what was possible, but those designs had to be manufactured in enormous quantities by factories that could not easily accommodate major changes once production was underway. The P-38 Lightning, with its outward rotating propellers and its wing fuselage fillet, represented a successful balance between performance and producibility. It was not perfect. The P-38K proved that better performance was achievable, but it was good enough, and it was available in the quantities that combat commanders needed. That combination of good enough and available won wars more reliably than perfect designs that existed only as prototypes or limited production runs. The nearly 10,000 P-38s built during the war flew with the propeller configuration that Lockheed's engineers had chosen in 1939, refined through wind tunnel testing and validated in combat. That configuration gave them the speed they needed to survive and to prevail. On that November morning in 1940, when Major Signa Gilkey climbed into YP-38 No. 5, neither he nor the engineers who had designed his aircraft fully understood the complex aerodynamic interactions that would nearly kill him moments later. The buffeting that began during his high-speed dive was not a failure of engineering. It was a revelation that the design had consequences the engineers had not fully anticipated. The same propeller configuration that provided gun platform stability and maximum speed was also creating airflow patterns that threatened to destroy the aircraft at high velocity. The solution, when it finally emerged from wind tunnel test number 15, seemed almost trivially simple. A fillet, a smooth blending of surfaces that changed pressure distributions and eliminated turbulence. But finding that solution required methodical testing, careful analysis, and a willingness to keep searching when easier answers proved inadequate. The engineers who reversed the propeller rotation from the XP-38's inward configuration to the YP-38's outward configuration made that decision for specific reasons related to aircraft stability and combat effectiveness. They did not fully understand all the performance implications at the time. The speed advantage emerged through testing and analysis, a beneficial consequence of a choice made primarily for other reasons. This is how engineering often works. Decisions are made based on the information available, and the full implications of those decisions only become clear through rigorous testing and operational experience. The fact that the choice proved correct, that outward rotation provided both the stability benefits Johnson sought and the speed advantages the aircraft needed represent success born from sound engineering principles rather than fortunate accident. The P-38 Lightning that emerged from this process of design, testing, modification, and refinement was not the aircraft that Kelly Johnson originally envisioned when he began work on the Lockheed Model 22 in 1937. It was better. It incorporated lessons learned through test pilot fatalities, through wind tunnel experiments, through combat experience, and through the accumulated knowledge of engineers who refused to accept inadequate performance when better solutions were possible. The outward rotating propellers and the wing fuselage fillets that characterized every production P-38 from the E model onward represented hard-won knowledge purchased through investigation and analysis. Combat pilots who flew the Lightning never thought about propeller rotation directions or wing fuselage pressure distributions. They thought about speed and altitude and firepower. They thought about completing their missions and returning safely to base. The engineering decisions that gave them the speed they relied on were invisible to them, buried in technical reports and wind tunnel data. But those decisions shaped their combat experience as surely as their training and their tactics. The 20 to 30 miles per hour that outward propeller rotation provided, compared to what the aircraft would have achieved with inward rotation, was the margin that allowed disengagement from unfavorable combat situations. That margin was life. Major Signa Gilkey survived his high-speed dive in November 1940 because he stayed with his aircraft until reaching denser air where the controls became effective again. The engineering investigation his near-fatal flight prompted led to solutions that made such dives survivable and controllable. Ralph Virden, who died when his YP-38's tail structure failed during a similar dive, did not survive to see those solutions implemented. But the lessons learned from his death and from Gilkey's survival shaped every P-38 that followed. Engineering is built on such lessons, sometimes purchased at terrible cost, always preserved, so that the next pilot, the next aircraft, the next mission has a better chance of success. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.